of momentum here as we head into this. Do you guys remember the alternating series error bound? So if we've got a converging alternating series and we find a partial sum, after, with however many terms, then the maximum error is less than or equal to what? The next term, the first neglected term, right? So that works great for alternating series, but kind of what this is all about here is essentially the question of, well, what if it's not an alternating series, because they aren't all alternating series, or what if we need a different error bound to help us describe something? What might we do? And so what we're going to be looking at here is what's called Taylor's theorem, and then more specifically down here you can see it. It's called the Lagrange form of the remainder. And this is something that will work on any series. It'll work on an alternating series, a non-alternating series, or series where the signs are like plus, plus, minus, plus, minus, minus, plus, just like inconsistent and sort of strange. This will work on any series to help us find the remainder or the error. And so Taylor's theorem, is essentially this: that f of x, and we're going to use a really important symbol right here, that f of x is equal to, right? It's not the little squiggly deal like the approximately equal to, but f of x is equal to, f of c plus f prime of c x minus c. Maybe you're recognizing this from last time, possibly, that this is the construction of a Taylor series. And then, f double prime of c over 2 factorial x minus c squared. And then you get this plus dot 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 plus an nth term. And then on the end, we've got this piece right here, r sub n x. So this is getting into what we're going to talk about here this morning, at least at the start, and that is the remainder. So what Taylor's theorem is essentially saying is that if you have a polynomial, right, f of c plus f prime of c times x minus c, dot dot dot, all the way up to a certain point, if we just add the exact remainder on the end, then we can say that our polynomial is equal to a particular sum, or in this case, maybe a particular function. The key is going to be how tightly can we pin down that remainder. It's not always going to be that easy, okay? And so we're going to be focusing on the remainder part of this. And this right here, let's see here. I think I'm going to actually scroll just a little bit here just so I can show you a little bit. Yeah, this is what I want to get to right here. And so the word most often, I threw that in there. The BC exam most often uses the Lagrange error bound. I don't know if that's going to be true this year because they're officially introducing the alternating series error bound. So maybe most often is not maybe appropriate now. Maybe it should just be like they use it frequently, but they'll use the alternating series error bound as well. This contains some pretty intimidating symbols. But we're going to pick these apart and kind of help you with what these symbols mean. I think you're going to see a relationship between this and the alternating series error bound. There is definitely kind of somewhat of a parallel. There are going to be some classic cases where it's definitely not the same, and we'll look at those too. So this right here on the far left, what we have is f of x minus p sub n of x. That's essentially saying that the actual sum minus your approximation based on your polynomial, right? So actual sum minus your approximation. Well, what is that another way of what are we describing there? If we take the actual sum minus your approximation, it's really what? Sorry? Residual, but yeah, we could call that an error, right? It's kind of the same thing. So, like if you approximated your height and you said, hey, I think I'm 70 inches tall, and then we actually measured you with a laser and we found out that you're like 70.5 inches tall, what's your error? Technically, aren't you subtracting to get that error? 70.5 minus 70 is 0.5. So that's all we're talking about. We're saying the actual measurement, whatever it happens to be, the actual number, minus your approximation, that is equal to the error. So I'm going to say this r sub n of x, that's the remainder, also known as the error. It's how far off you are. And here's where we get into this Lagrange form of the remainder. This is less than or equal to, and then it gets a little scary. Here we go. X minus c to the n plus 1. So C is your centering point, just like we used with we constructed the Taylor series, the C is the centering point, just like it was before. X is the number that you were trying to approximate. X is the number that you were trying to approximate. So I'll put APX for X and CTR for C. So C is the centering point. X is what you're trying to approximate. And then N plus 1, well, we're basing our approximation on N, so this would be kind of the N plus 1th term. You might say, oh, this is just the next term then, right? Not always, because not always is the next term just going to be N plus 1. We've already seen with sine and cosine, the next term is actually plus 2, isn't it? Remember the powers on sine and cosine? For sine it goes 1, 3, 5, 7, 9. On cosine it goes 2, 4, 6, 8, 10. So like the next term won't necessarily always be N plus 1. And then N plus 1 factorial will be your denominator. Hopefully that's pretty straightforward. We all have talked about factorials a lot. And then the one that usually gets people thinking is this last one right here. The maximum value of the N plus 1th derivative of Z, and Z is defined as some number between C and X. So Z is some number between C and X. This might seem horribly complicated. We're going to do 3 examples here, and I think that we'll be able to boil it down to some pretty simple stuff. Okay, so X minus C to the N plus 1 factorial times maximum value of the N plus 1th derivative at Z. So here's what I want to do for you. There are essentially 3 parts to this, and I'm going to highlight these 3 parts like this. Yellow and blue and orange right here. So with this Lagrange form of the remainder, the yellow part and the blue part are very formulaic in that if you know what numbers get plugged where, it's going to be the same sort of thing every single time. This gets plugged here, that gets plugged there, and this gets plugged here. All those things are very much plug and chug. The thing that's highlighted in orange, to some degree or another, there will be a gray area, sort of like an inexactness assigned to it. And the examples that we're going to do, we're going to go from the first example. There's not going to be too much inexactness to it at all. It's going to be pretty concrete. The second one will be a little less exact, and the last one will be the least exact. It'll be the most gray. Okay? Because, listen, aren't we uncomfortable with things, especially in math, that are inexact? I mean, come on, we want to know the answer is this. And the answer will still be this. It's just that our reasoning and kind of our thought process will have to be a little broader, have to be a little more flexible at times. And you'll maybe see what I'm talking about as we go through these 3 examples. So I'm trying to go in order of like concrete, and I don't know, I got to think about this one a little bit. That'll be kind of the order we go in. Can you accept that? I hope you can. All right, so let's take a look here. Keeping in mind that little formula, that is something you got to have memorized. But again, I hope that it's a conceptual thing as opposed to memorization just purely for memorization's sake. Although if you want to make a flashcard, memorize it. That's great. It's called the Lagrange form of the remainder. And here is example number 1. Come on. There we go. Okay, so this says, hopefully some of this is very familiar. It says the 3rd degree Maclaurin polynomial for e to the x is given by p sub 3 equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial. So we actually, I think we proved that last time at some point. So that's just like a given. And then it says use Taylor's theorem to approximate e to the 0.1 by using p sub 3 of 0.1 and show that the max error is less than 5 times 10 to the negative 6. So we're going to do, it's 2 steps here. We're going to use Taylor's theorem to approximate that. So what I would say is this. The notation I'd use would be e to the 0.1 is approximately equal to p sub 3 of 0.1, and that equals, I'm simply going to plug in a 0.1 for every time I see an x. So this is going to be the polynomial approximation for e to the 0.1. So it would look like this. 1 plus 0.1 plus 0.1 squared over 2 factorial plus 0.1 cubed over 3 factorial. And just for argument's sake, often you won't have a calculator for these sorts of problems, but with these sorts of numbers, if you're expected to go all the way, which for now, let's do that. Let's use your calculator and let's actually approximate, or let's calculate this out. So 1 plus 0.1, so it's going to be 1.1 plus some other itty-bitty decimals. So take just a moment and do that, and then we'll talk about the error. And the error, I would say this step right here should not feel terribly new. We did this last time we met, but the Lagrange error bound is new. So 1.10516. It looks like the 6 is repeating. Something like that? Okay, cool. You guys get the same thing? Okay, awesome. So that's not exactly e to the 0.1, right? Because we used a polynomial approximation, the keyword being approximation, so we know for sure we're off. And so the idea here is, how can we prove that the error is acceptable? And apparently we are told that, and we're supposed to show that the maximum error is less than 5 times 10 to the negative 6. So, like 5 times 10 to the negative 6 sounds like a really tiny error to me, right? That's like 0.5 zeros and then a 5. Seems pretty small. We're supposed to prove that the error for this is at most something less than that, right? So how are we going to do this? If this were an alternating series, we could use the alternating series error bound and say, hey, we cut it off when n was 3, so let's see what the first neglected term would be if n was 4. But this is not an alternating series, so we can't do that. So we're going to have to use the Lagrange form of the remainder, and here's how we could do that. I would say something like this. E to the 0.1 minus p sub 3 of 0.1, the absolute value of that, so this is expressing our error. The actual value minus our approximation, that's our error, is less than or equal to, and we're going to use the Lagrange form of the remainder, so it was x minus c to the n plus 1. So what do you guys think our x value would be? 0.1, right? That's the number that we use to try to approximate. So I'm going to put this in as 0.1 minus c. C is our centering point. What was our centering point for this polynomial? 0. That's right. It's Maclaurin, and you can see that all the x's are just x's instead of like x minus 2's or whatever. So 0.1 minus 0 to the n plus 1. So what was our n?
3.
3, right? We use the n equals 3 polynomial, right? So 3 plus 1, of course, is 4. And that plug and chug part is done. In the denominator, it's n plus 1 factorial. So we already know what n plus 1 is. So it would be 4 factorial. And then we need to multiply this by the max value of the n plus 1th derivative somewhere on our interval between x and c. So let's do this first. We know that the function that we are trying to approximate is for e to the x, right? So I chose this one on purpose to start us off with, because whether it's the n plus 1th derivative or the n plus billionth derivative, if our function is e to the x, that derivative is e to the x. Okay, so we know, I'll just write this down here below and maybe I'll erase it in a second. I know that my n plus 1th derivative will always be e to the x. So we're trying to figure out what goes in here for this max value of the n plus 1th derivative. So the interval that I have to deal with is the interval from 0, which is our centering point, to 0.1. Right? So this z that was mentioned in that formula, z is somewhere on that interval. It could be either endpoint or some number in between. So like I said, there's a little bit of a gray area to this, but I think once we think about it, most of the gray will disappear. Can you think about the graph of e to the x? What characteristic do you recognize that might be appropriate when we talk about like maximum values of things when it comes to e to the x? E to the x is always increasing. E to the x looks, like you mentioned, increasing. It's something like that, right? So if we kind of zoom in and say, well, this is, of course, 0 right here, and maybe this is 0.1, well, where would the maximum value of that occur? At the right endpoint, wouldn't it? Because we know, hopefully, that e to the x is always increasing, and so the max value of that n plus 1th derivative would have to happen at 0.1. Does that seem reasonable? So we can really tighten this up really well by saying, hey, I think the max value of the n plus 1th derivative would be e to the 0.1. We reached that conclusion just based on knowing what the graph of e looks like and knowing how to, what the max value would be on an interval to always be the right endpoint. You can imagine some of the graphs we'll look at in the future won't be quite so cut and dried. We're going to have to use a little more of a thought process to arrive at a conclusion. So I'm going to erase all this extra stuff down here below, but I think that it's still good to maybe write that down to think about where that e to the 0.1 came from. So again, often you won't have the calculator to do this, but let's go ahead and use the calculator just so we can kind of satisfy, hopefully a correct answer here. So if you would, let's do, 0.1 to the 4th, divide that by 4 factorial, and then multiply that times e to the 0.1, and let's see what that number ends up being.
You don't have to multiply the e to the 0.1 times any z.
Times what?
Times any z. Like, I'm just confused by the z.
So the z is the input, so it's like the n plus 1th derivative at z.
Oh.
So z would be your input, and so we're just saying, the reason why I put a z there is because what that number z is, as far as like deciding what the what value is going to maximize that n plus 1th derivative, here it was pretty cut and dried because we know e to the x always increases, but it won't always be, hey, it's the right endpoint or the left endpoint. It'll be sometimes some number in between, and we won't even be able to really truly pin that down either. So we just use some vague input like z.
Okay, so like just in this case, it has like an actual value, but like in the future.
We might have to really approximate that. It might get kind of fuzzy. We won't be able to say it's definitely this. We might be able to say, well, it's definitely less than this, or it's definitely not that.
Yeah.
But we might not be able to pin it down quite so tight like this. Okay, so when you guys multiplied all that out, what'd you get? Say again? 4.605 times 10 to the what? Times 10 to the negative 6. So you can see that by the skin of our teeth, we've proven it, haven't we? It's pretty tight.
Oh, less.
5 times 10 to the negative 6th versus 4.605 times 10 to the negative 6th. There's a pretty tight window there that we're in. We're just barely less than the error that we were supposed to be less than. So at this point we would say, which is, this number that we just calculated is truly less than 5 times 10 to the negative 6th. So in other words, we've proven the thing that they asked us to prove. Now, in maybe more of a realistic scenario, if we were told that 5 times 10 to the negative 6 was the max error, and we did something like this, and we calculated our max error, and it turned out that our max error was too big, what could we do to improve our approximation?
Go another term.
Yeah, do another term or two, and then maybe you'd see, okay, yep, actually, now that we are, 2 terms out further, we are below the max error. So you can see that, if this truly is a converging series, those terms would get smaller and smaller, and so that error would get smaller and smaller. Is it a little less terrifying? I know when you first see those symbols, it's kind of like, oh my gosh, z's, and actually put max in a formula and all this stuff. I know it can be a little scary. Let's take a look at a different one, since you guys don't seem too intimidated. So let's take a look at it. This will be, I think, a nice review for you, and then we'll also catch this remainder thing, this Lagrange error bound to, let me just get a little bit better. There we go. Okay, so it starts off by saying find p sub 3 of x be the third degree Taylor polynomial about x equals 0. So if I say, let's see if you guys, I think you probably remember this. If I tell you that you got a Taylor polynomial centered at x equals 0, how could I say that much quicker? Maclaurin polynomial, right? It's saying the exact same thing. Sometimes it'll be worded like this. Other times it'll just say Maclaurin polynomial. You want to recognize both. So what they're really wanting us to do here is construct this all the way out to the third degree. So this will be a nice review from last time. That's kind of why this is here where it is. So let's try it out. I'm going to say p sub 3 of x is equal to, the very first term should be just f of 0, right? So we can maybe mentally do this. We could say, all right, well, if x is 0, it's just 5 times 0, which is 0, so it's sine of pi over 4, right? Which is what? Root 2 over 2. All right, so we're on our way. Our first term is root 2 over 2. It does get a little more challenging, but we're off to a good start. Okay, so the next term is going to be based not on f of 0, but on the coefficient will be f prime of 0. So I'll just write some little notes down here about this. So f prime of x would equal what? Good job. That's right. Let's not forget the chain rule in all of this. So 5 cosine of 5x plus pi over 4. Okay, so then f prime of 0 would equal what? 5 root 2 over 2. That is correct. So plus 5 root 2 over 2 times x. Okay, we're up to first degree, so we're halfway home. We need second and third degree. So to find second degree, we need second derivative. Say that again, Hayden. There we go. Good. So again, chain rule comes into play there. So f double prime of 0 would be what? Hopefully you're starting to see the pattern. There you go. So this is minus, so it'd be minus 25 root 2 over 2 times x squared over 2 factorial. You guys remembering this from last time? Okay. So we're down to our final term. So the third degree term will be based on third derivative. So f triple prime of x, what's 5 times 25? 125. So this would be negative 125 cosine 5x plus pi over 4. So then that means that f triple prime of 0 equals negative 125 root 2 over 2. So our final term would be minus 125 root 2 over 2 times x cubed over 3 factorial. So that's our third degree Maclaurin polynomial for that sine of 5x plus pi over 4 function.
Is that all it wants? Does it want us to like...
On part A, yeah, just basically find p sub 3 of x. So I think we've done it.
Simplify it?
Oh yeah, great question. So it's kind of the standard thing with like a multiple choice. You're going to have to simplify it. On an FRQ, you may or may not. Like I can think of times when simplifying it would make a big difference because maybe on later steps the simplification will really help you. But if that's not the case, then yeah, just leave it like this. Yeah. Any other questions? So hopefully good review for you. Take a look at B now. B, of course, is what we're talking about today. It says, use the Lagrange error bound to show that f of 1/10 minus p sub 3 of 1/10 is less than 1/100th. So what they're really saying here is that if you plug in 1/10 into sine of 5x plus pi over 4, and you were to get the actual value, and then if you were to plug 1/10 into our polynomial and get that approximation, show that your error, you'd be off, show that your error is less than 1/100th. So again, we're going to do this without a calculator. So far, we haven't touched the calculator. We will continue to not use a calculator. So here's what we're going to do. We're going to say f of 1/10, the absolute value of it, minus p sub 3 of 1/10 is less than or equal to, here we go. Remember the numerator is x minus c to the n plus 1. So what's our x value? 1/10, right? That's the number we approximated with. So it's going to be 1/10 minus c, and c would be 0. That's our centering value. So 1/10 minus 0 to the n plus 1. So what was n? So kind of like the previous one, n plus 1 would be 4. So 1/10 minus 0 to the 4th over, again, this is part of the very formulaic part of this. n plus 1 factorial. So we know that n plus 1 is 4. So some of these numbers are going to feel really similar to the one we did just a second ago. But of course, now we get to this n plus 1th derivative's max value. This is a little less clear. Number one, we don't have a calculator available to us, so we can't graph that n plus 1th derivative and figure out exactly what that looks like. We are talking about the interval from 0 to 1/10, but perhaps the most important thing is that we are talking about the n plus 1th derivative, and it involves sine or cosine. That's going to be super key. So we know what the third derivative was, right? I'm going to go back up here, and now that I think about it, we probably would want to calculate the fourth derivative, shouldn't we? Knowing that we're going to be trying to find this error. So the n plus 1th derivative would be the fourth derivative. So I would say the fourth derivative, I'm just going to put this up here in a different color. The fourth derivative, gosh, what is 125 times 5? 625. And of course the derivative of cosine is negative sine, so I think the negatives would cancel out. So it'd be 625 sine of 5x plus pi over 4. Okay, so here's where, like I promised you, the first one that we did was pretty concrete and fairly exact. This one is going to be a little fuzzier, but in the end we'll be able to pin this down okay. Like I think it'll be acceptable, I hope. So here's my question. This is the fourth derivative. Our interval is from 0 to 1/10. We know a little bit about sine, but I mean, if you look at what's going on over here, hasn't this sign been shifted a little bit? It's actually been shifted pi over 20 to the left. Yikes. I'm not excited about that, are you? You shouldn't be. So as far as like 0 to 1/10, I mean, you could plug in a 0 here. I think if you plug in a 0, you'll maybe get a pretty concrete value, but then, hey, what about the 1/10 thing? Where's this all going to go? We're going to have to think pretty generally here, okay? We can't really pin this down exactly, so we're going to have to give ourselves some room for error, literally. Can you sort of picture this graph in your head a little bit? Not perfectly, but can you sort of picture it? You know what sine looks like? You know what cosine looks like? So a regular sine graph, the values, the y values, oscillate, right? Between what and what? Negative 1 to 1. The parent graph goes from negative 1 to 1 to negative 1 to 1, blah, blah, blah. Well, this fourth derivative oscillates too, just like that one. Except the oscillations are a little different. What is the oscillation going between for the fourth derivative? 625 to negative 625. The amplitude, right? 625. So looking at this, without having like perfect knowledge of what this graph looks like, especially on the interval 0 to 1/10, seriously, what could we say for sure? Like we could bet all of our money and our life that we know what the max value of this fourth derivative is. 625. Can't you say with absolute certainty that the most that could be is 625? So that's what I'm putting. Is 300 enough? Maybe, but I don't know. Is 400 enough? Probably, but I don't know. I know for certain that 625 is the absolute biggest that this fourth derivative could possibly ever be. Does that make sense? Now, we could run into problems with this. We'll find out shortly here if we're going to run into problems with this, but I'm going to tell you right now that I would put 625 here simply because I can defend that. I mean, seriously, if you put 300 and I say, no, prove it. Prove that 300 is the biggest it could be on 0 to 1/10. You might be able to do it, but it's going to take you an incredible amount of work. And please know that on one of my tests, the AP test or whatever, we're not going to expect you to do like extreme arithmetic, right, to prove something like this. So test your handles up first and we'll get Grace next.
So basically, how do you know that it's going to equal that though?
I don't know. See, that's the thing. This is where it's a gray area. I do not know that on the interval from 0 to 1/10 for certain that it hits 625. In fact, I'm pretty sure that it doesn't.
Yeah.
I'm pretty sure that it's something less than that. But I don't know for sure what it is, and so I'm going to go with what I can say with absolute certainty. It cannot possibly be more than 625. I know I'm pretty sure, very confident actually, that it's something less than that. But I mean, think about it. Didn't we mess with the period of this sine graph too? We divided the period by 5. So we start at negative pi over 20, and the period is 2/5 pi. So really, can you be for certain that you can say, well, I think it's actually 400? I don't know. That's pretty shaky, right? Grace, your question. No. See, that's the thing, is z is some number between that you can defend, right? It needs to be for your own, confidence that you got it right. You need to be able to say, well, gosh, there's a lot of uncertainty here, but I am certain about this. I'm absolutely, totally convinced that 625 is the highest that that fourth derivative could be. So, let's see how this works out. Remember, no calculator, right? So we are going to do some arithmetic. So I'm going to try this. So I'm going to continue on here and say, all right, well, this is less than or equal to, so 1/10 to the fourth. That's 1 over 10,000, right? So 1 over 10,000. And then 4 factorial is 24. And that's times 625. You know what? I take back my 10,000 thing. Here, let's do this. I'll keep my 24 perhaps. So I'm going to write 1/10,000th. I'm going to write it as 1/10 times 1/10 times 1/10 times 1/10. I'll put my 24 right here. The reason I'm going to do that is I think I can cancel this a bit with the 625, right? So the 625 has how many 5s?
125.
Well, 625 is 5 to the what? 5 to the fourth, isn't it?
Oh, yeah.
I'm just going to show you some arithmetic here. So if 625 is 5 to the fourth, there's 4 1/10ths, aren't there? So wouldn't each of those 5s cancel partially with each of those 1/10ths? Okay. So 625 is really 5 times 5 times 5 times 5. So wouldn't this 5 cancel with this to make it 1/2? And wouldn't this 5 cancel with this one to also make it 1/2? And then another 1/2, and then another 1/2. Yeah? So what's 2 to the fourth? 16. Yep. So it'd be 1/16 over 24. So that's really 1/16 times 1/24. Oh, come on. There we go. So what's 1/16 times 1/24? Might have to do a little bit of scratch arithmetic here. Say again? 144? Say it again?
Would it be 24 over 1?
Well, so yeah, this is 24 over 1. So I got 1/2 divided by 24. So I'd go copy the 1/2 dot and then flop the 24. Say again? 384? Okay, so 1 over 384. And is that less than 1/100th? By a pretty wide margin, isn't it? So I just proved it. Now, here's where people get stressed. They're like, oh my gosh, how am I supposed to do that arithmetic without a calculator? You can. You're going to have to be creative and look for the cancellations. I noticed that 1/10,000th didn't like that. So I started canceling my 1/10ths with my 5s. Please know that something like this very well could show up. The arithmetic is sort of intense, but let's just be honest. It's not a question of whether you can or can't do it. It's a question of whether you'll discover what to do and do it in a timely fashion. So, question, Tess.
Can you just go back a little bit when you started canceling? Because 1/5, I feel like there should be 2 5s left.
Well, there was 4 1/10ths, right?
Yeah.
There was 4 of them, and there were 4 5s.
Yeah, so wouldn't
So-
1/5 or two fives cancel out one time.
5 times 5 is not 10.
But like 5 times 1/10 is 5/10, which is
1/2.
1/2.
So what you just said is this 5 is gone.
Yeah.
This 1/10 just became a 1/2.
Yeah.
And then 5 times 1/10, same thing. 5 times 1/10, same thing. 5 times 1/10, same thing.
Okay, so then it's 1/2 times 1/2 times
Yeah.
1/2.
Exactly.
Okay.
Yeah. Anybody else? Jasper. How do you find C? C is your centering point, so that should be given to you. So if you look back earlier, it said make the Taylor polynomial centered at x equals 0. That means that your C value is 0. Sorry, Jasper?
Where does it say on that?
Say again?
Where does it say on that?
At the very top. Let P sub 3 of x be the third degree Taylor polynomial about x equals 0. Anybody else? Okay, let's do our last one. The last one is right here. Example number 3. Okay, so this says the fifth degree Taylor polynomial for some unknown function, g of x, about x equals 0, is given by that p sub 5 of x, and gives you the terms there. Then it says the graph of g with a 6 up there. Of course, that means the sixth derivative of g is shown below. So part A says, use the fifth degree Taylor polynomial about x equals 0 to estimate g of 1. So I'm going to write this. This is similar to the previous one. We're going to estimate g of 1, so I would write g of 1 is approximately equal to, and now we just plug a 1 in for x. So 1 plus 1/2 plus 1 over 72 plus 1 over 3,600. Now please notice, this is not an alternating series. It's not an alternating polynomial. It's not an alternating series. And so, because it's not an alternating series, we can't use the alternating series error bound. If we want to find an error, we're going to have to use Lagrange form of the remainder. And that's what part B is all about. It doesn't say use Lagrange form of the remainder, but we have to simply because we don't have an alternating series. Good? Question?
So, if it was like plus, plus, minus, plus, plus, that wouldn't be an alternating series.
Still use Lagrange. Yeah. Anybody else? Okay. Oh, question, yes.
If it was an alternating series, could you still use the Lagrange? And then
You could. Yeah, the Lagrange will work on everything. Regardless of the arrangement of the signs, it'll work on everything, but alternating specifically has to be plus, minus, or minus, plus, minus, plus. Good question. Anyone else? Jared, you still with us? I know, long weekend. Stay focused as best you can. Okay, so explain why your estimate differs from the actual value by less than 1/100th. So this one will be the most gray area we've done. And I'm going to actually use a little bit of the area up here on A just so I can fit this on the screen well enough. Okay, so we've got to use Lagrange form of the remainder. And so here's how this is going to go. I'm going to say something like this. Absolute value of g of 1 minus p sub 5 of 1. That's my error. So the actual value of g of 1 minus my polynomial approximation at 1. I'm trying to describe my error. And I'm going to say that this is less than or equal to x minus c to the n plus 1. So what is my x value here? 1. So 1 minus, what's my centering value? 0. So 1 minus 0 to the n plus 1, and n plus 1 would be 6, right? Because the fifth degree is what we use to approximate, so it's going to be 2 to the 6th. Oops. No, see, that's what I wanted to. This is where we get to this point. With an alternating series, which this is not. With an alternating series, though, the error is always less than or equal to the first neglected term. This is not an alternating series, though, so we cannot say that. So the Lagrange error bound is based on the, essentially, what's going on at the n+1th stuff. And so since we used a fifth degree to approximate, then all of our n+1s will be 6s, not 7s. So the Lagrange error bound is not the first neglected term, it's just the n+1th stuff.
Okay, so if the series was alternate, we could just use a different
You could. Yep, you could just use a different error bound. So then n+1 is 6, so it'd be 6 factorial times. So the max value of the n+1th derivative, convenient, right? They gave you the 6th derivatives graph. Maybe now you see why. It seemed a little weird at first. But they gave you that 6th derivatives graph so that you could then use it to help you find your best approximation for the max value of that 6th derivative. So I'm looking at this. My interval, of course, my centering value is 0. My x value is 1. So we're looking for the max value of the 6th derivative on the interval from 0 to 1. What could you say and defend it with extreme confidence? What's the max value? 6.
But it doesn't go like 6.
I'm saying that
You can defend it.
I am saying that I can absolutely defend that the max value of this n+1th derivative cannot possibly be more than 6. Right? 6 is right here. I'm saying that the max value can't be above 6, can it? Now listen, here's where you get into this. And I'm okay with this discussion. Like what if somebody were to say, no. I think it's 5.7. Really? Can you truly defend that?
Yes.
Really?
Yes, because you know that halfway between 4 and 6 is 5.
So you're telling me that your perception of relative distance is
I mean,
perfect?
that is what rulers are for.
Really? So you want to be my guest? I'll let you use a ruler on one of my tests, or I don't know if they'll let you do it on the AP test. Hold on, I'm still discussing with Hayden. Hayden, I don't think there's any way you can truly defend it and say, hey, well, you're giving me a lot of credit for one. You're saying, Mr. Anderson, you have perfectly drawn this graph. So exactly that I can estimate down to the 0.5 millimeter what the value is. That's a little unrealistic.
Yeah.
I don't think you can really, truly defend that. Test, go.
Well, I was just saying, it's never going to actually equal 6. So
That's the point. It's always going to be below 6, isn't it?
yeah.
So for me to say, think about what I'm saying here is, I'm called on to find the max value of the 6th derivative. So I'm telling you, I don't think I can do that. But I can tell you this, it's not bigger than 6.
Okay.
That make sense?
Yeah.
I can defend that. Now, if we want to go down Hayden's Road and say, well, I think it's 5.72, and I got my ruler out, and here's how I can prove it, that is really shaky, and it may or may not be valid. But for me to say, there is no way on earth, based on what I see on this graph, that it could possibly have a value higher than 6, I can defend that. I can defend that.
So, like, technically then if you really have hardly any idea about a function, like where it is, you could just say, like, oh, I'm just going to say 100. Because it
Well, you got to be careful about that, because if you pick something too high, then the error that you're supposed to be within is not going to work out. Right? I could say, hey, you could take this to an extreme and be like, well, I think that there's no way that this 6th derivative could be more than 10 billion. And so for that last little factor in there, I put 10 billion. You know what? That's very defendable, isn't it? But then when you try to say, all right, well then, is my error going to be less than 1/100th? I have a sneaking suspicion that you won't be able to prove it using your 1 billion estimate for the max value of the 6th derivative. So you want to get as close as you can, but still be able to defend it.
So it's okay if your max value is something that's never actually going to be.
Isn't that what we did with the previous one, though? Didn't we say with 625 of sine 5x plus pi over 4? Like we said, we have really, without using a calculator, we have no realistic idea exactly what the max value is. But all we said is, well, I know for sure that it's something less than 625.
Okay.
That's kind of what we're doing here. We're saying, well, man, I don't know. I mean, it looks to me like the max value happens right in there somewhere. So, like when x is maybe like 0.68 or something like that. And so we get into all these little, details with decimals, and it's like, holy cow. No matter how I zoom in and no matter how good I am with a ruler, I still don't know truly what it is, but I do know for sure that it's less than 6. And so what that means, then I think I can comfortably say times 6.
Okay.
If you want to put 5.8 and take your chances, if you do that, I will actually get out the calculator and see if you are correct. And if you're not, you won't get credit for it. So my point is, don't be cute and be like, oh, well, I think it's 5.82. I will never call on your perception of the relative locations on a graph and have that be the difference between success and failure. It's like, hey guys, I'm sorry, Hayden is the best. She hit it right on the nose. It really is 5.801269843
When you're finding.
pi square rooted or something like that. She got it, and the rest of you are terrible because you couldn't figure that. That's ridiculous. But I think it's very reasonable for me to say, hey, there is no chance that it's higher than 6. So I'm going to put my max at 6 because I can defend that comfortably. Okay, so Will and JJ, did I get, because you were going with the 1 billion idea? Yeah. Yeah, so if we didn't have like we need this error to be less than 1/100th, then yeah, kind of the door's wide open on, I went with 1 trillion. Because I can defend that. You want to tighten it up as tight as you can, but have it still be defendable. That's going to be the only way that you can sneak it in that little error window. So let's see what happens. Kind of nice here, if you do pick a 6, did you notice that the 6 cancels off with the front of the factorial? Okay. So, and then, gosh, 1 to the 6th.
120.
1 to the 6th is 1.
I know, I was on the bottom.
Oh, gotcha. Okay, so 1 over 5 factorial is, yep, sure, 120. And so looky there, 1/120th is truly a little bit less than 1/100th. And so we've proven it. Notice it says explain why. Sometimes it'll say show that. Like we're essentially proving something. And once we've gotten to that number, we can prove it, then we've proven it, and we're done. Okay? Has your comfort level risen with this from that first encounter with, oh my gosh, look at that thing. It's terrifying. Okay, cool. 5 factorial is 120. So we took this right here. I mentioned it briefly. I apologize for that. Isn't 6 factorial 6 times 5 factorial? So what I said is this 6 cancel with that 6. And then 5 factorial is 120. And so 1/120th we know is less than 1/100th. Pretty tight margin there, but it's still gets in there. Any other questions? Okay, fantastic. Let's move on. Let me get to here. There we go. So the next little topic is something that we have talked about quite a bit and dealt with some. I want to use a calculator to kind of help motivate this a little bit. So if you would take just a second and watch this with me. I am going to put in a couple of functions. My first function is going to be, let me make sure I'm still recording here. I am. All right, so my first function is this. 1 over 1 minus x. And I'll just zoom 6 that. As you might suspect, there's a vertical asymptote at 1. There you go. 1 over 1 minus x. So do you guys remember that this is, we finished with this at the very end last time, this is the sum of a geometric series, right? 1 over, remember a over 1 minus r? 1 over 1 minus x. So maybe you remember this, maybe you don't. We'll go back over this again for sure. But the polynomial approximation for this is this. 1 plus x squared plus x cubed. And at the end I made that, I don't know, I felt like it was an amazing thing to notice that that's the geometric series, right? It's basically times x each time, right? It's x to the 0, then x to the 1, then x to the 2, then x to the 3. And so this should be a good approximation. And in fact, if you look at the graphs, you hit the graph here, then you see this red graph show up, and looky there, it kind of is a decent approximation, right? So then what's the rule of thumb? Like if you've got an approximation and it's not as good as you were hoping for, how could you make it a better approximation? More terms. So let's go back. These are easy terms to add in here. So I'm going to go overboard a little bit. I'm going to come out here and say, I want my approximation to be awesome. So I'm going to go with this, plus x to the 4th plus x to the 5 plus x to the 6th plus, I'm just going to, like I said, I'm going to go a little crazy here. How about x to the 8th You guys want to go all the way to 10 with me? Boy, that was really encouraging. I'm going to 10, and I'm going to pull a Buzz Lightyear and go beyond. How about 11? So I started off with 3rd degree, and I just added a bunch. I'm all the way up to 11th degree. So wouldn't we expect the approximation to be quite a bit better as far as mimicking this graph? Let's check it out. So here's the original graph. This is 1 over 1 minus x. And it's taking forever because I think it's graphing these simultaneously. Here in just a moment you should see the other one pop in here. There it is. It's like watching paint dry. Come on, graph, you can do it. You'd think that my computer would be really fast, right? Because it's way more powerful than your calculator, but interesting. So it did get better, didn't it? Did it get as better as you thought it would? It wasn't that much of an improvement. So I want you to think about this. Truth of the matter is, like if you look at this, I'll outline it right here. If you look at this as far as like the interval of convergence goes, we're basically going from right here to right about here, right? -1 to 1-ish. The truth of the matter is, if you've got a lot of time on your hands, you want to do this, you could. But you could go back to your y equals, and for my 1 plus x squared, you could take it out to like the 100th power. You could have 101 terms, or you could even go out to the 300th power. I don't know, whatever your calculator can take. And you would find that no matter how many terms you add, that interval where they kind of converge is not going to get too much better. It's going to remain roughly between -1 and 1. Now let's talk about why that is. It's a geometric series, right? So what numbers work for x in a geometric series? Isn't it just the fractions? If your common ratio is like 1/4 or -2/3 or whatever, it's only the numbers between -1 and 1, and so that's why the graphs only really converge between -1 and 1. Didn't we see that that was not true with sine and cosine? Remember with sine and cosine when we did, I think we did sine at the very start of this. Remember how when I added more and more terms, did the interval of convergence go from this to this to this to this to this? It got wider and wider and wider. So the characteristic we see here with the geometric series is not always going to be true for all functions. In fact, with sine and cosine, if you add in enough terms, it just continues to get better and better and better. The interval gets wider and wider and wider. So my point with all of this is that certain approximations will have a wide variety of intervals of convergence. So we're going to look at how these intervals of convergence work, and we're going to kind of finish with this and do a bunch of stuff with various series. So we're going to do a couple of thoughts, maybe one example on this, and then that'll be our time. This has gone by fast for me. I hope it's series. Power series is just a general way of talking about Taylor polynomials and Maclaurin polynomials. They're all power series, right? Because the exponents go 1, 2, 3, 4, 5, or 1, 3, 5, 7, 9, or 2, 4, 6, 8, 10, or whatever it happens to be. So it's series where the power is increasing. And so, this right here, centered at 0, this is a Maclaurin polynomial construction. Centered at C, you could say this is a Taylor. Right? Those are those constructions you see where a sub 3 is just some coefficient based on the whole factorial thing in the f prime or f double prime. But the point with this is, with power series, convergence is something we want to measure. So there's 3 possibilities. 3 possibilities are this. The series might only converge at the centering point. That might be the only spot that it ever really truly converges. Or there could be a certain radius of convergence, which we just saw with that geometric series, where there's just kind of a very limited domain where we get convergence. And then with some, like sine or cosine, we get a series that converges for all x if we just have enough terms. Okay, so the way that we find and determine the radius of convergence as well as the interval of convergence is something that we've practiced a little bit, and that is the ratio test. So there's a little review of the ratio test right there. So just as a reminder, the series converges absolutely if you calculate the limit and you get something less than 1. The series diverges if you get something bigger than 1, which of course includes infinity. And then the ratio test doesn't tell us anything if you get exactly 1. So that's just a review of the ratio test. We're going to use that right here, right now. You ready? I think we have time for one example, maybe an intro to another one. So let's check this out. As with most math, kind of weird just to talk about it. It's a lot easier to try to do it. So here we go. Take a look at number 1. It says, find the radius of convergence for that series right there. So what this is basically asking is, from the centering point out to the right edge, or from the centering point out to the left edge, how far can we go with our x values and expect convergence? Yes, it's alpha. So here's what we do. We're going to set up the ratio test. It's almost as if I can tell what's happening. Okay, here we go.
Had any experience with God's supernatural gifts? Come and join us for this discussion in the Arts Center upper lobby. Food is provided for all Alpha participants.
So n plus 1 term, right? We just substituted n plus 1 wherever we see an n. So it's absolute value, so what can I just ignore? The alternating thing, right? So I'm just going to ignore that. But in place of a n, I'm always going to put n plus 1. This is the top of our ratio. So it's going to be x to the 2n plus 2. Is it okay that I distributed it right away? 2 parentheses n plus 1? Okay. I just want to make sure I want to make sure you got it. I'm sorry if I disappointed you. I appreciate your honesty. Or your fake honesty, I should say, Allie Blaine. All right, so then the other n gets replaced by n plus 1. So again, we distribute the 2. We get 2n plus 2. Still doing okay? All right. So then I'm going to automatically copy dot flop this. So that'll give me 2n factorial over x to the 2n. I close it up like that. Now remember, we are looking for an interval of convergence. And so we want this to be less than 1. So I'm going to go ahead and put less than 1. We're looking for where this converges. We're not just going to be like, hey, let's explore what's going on. We are specifically saying, for what x values will this series converge? So like we've done before, let's go ahead and do a little bit of work with simplifying stuff on the inside. Limit as n goes to infinity. And let's see here. With the x's, when you're dividing like bases, you subtract your exponents, right? So x squared, all right? So x squared goes in the top. And then with the factorials, I'll put it like this. 2n plus 2 factorial would be 2n plus 2 times 2n plus 1 times 2n. Can I go dot, dot, dot for now? And then up here is 2n factorial. Well, isn't 2n dot, dot, dot kind of like 2n factorial? So then I would say that this and this would cancel out. Still hanging in? Okay. So now we're ready to do our limit, and I think we'll find a pretty interesting discovery here. With our limit, remember, we want to be really careful about our variables. Its limit is n goes to infinity, not some other variable. It's incredibly important that we realize that it's n going to infinity, not some other likely candidate that you see up there. It's specifically n. Let's think about what's going on here. We've got 2n plus 2 and 2n plus 1 in the denominator, and we're told that n is getting gigantic. Does it really matter what x is? No. Because it's going to be over something getting huge, and so the overall value of that fraction will be 0. So the reason why this is an interesting result is the x essentially got infinityed right on out, didn't it? So what this is basically saying, this is a huge thing to say, it does not matter what the x is, the ratio will always be less than 1. It doesn't matter what the x is. So what do you think that means as far as radius of convergence? Always, right? There is no x that doesn't work. So I would say that our radius is infinity. There is no x value that won't work. They'll all work. We'll close with this. Is there any chance that anyone recognizes that series? Soon you will want to all say, yes! We'll get there soon. This will be your first opportunity. Does anyone recognize it? Don't be embarrassed if you do or don't. Wouldn't all of the exponents be positive? Or, what am I saying? Wouldn't all the exponents be even? And wouldn't the terms go negative, positive, negative, positive? So let me write it. What is it? Which one? It's cosine. This is the Taylor polynomial, or the power series now, for cosine. And remember how I showed you with sine, similar with cosine, the more terms you add, the better and better and better the radius of convergence gets, right? And so you could say, based on that, if you have the number of terms going to infinity, the radius of convergence will be infinity. It would be a perfect representation. That's not true of geometric series. It is true of cosine. Geometric series has that very limited interval of convergence. Cosine is actually infinite. So we'll keep exploring these tomorrow. Have a wonderful day.